We've covered Merton and portfolio optimization, so we'll just quickly recall that. We've defined a problem, which is where we've got a stock that evolves according to a geometric Brownian motion, and then we've got a bank account that gives us a fixed interest rate R. Okay, and we can either save some money in the bank account and receive an interest of R, okay, or we can invest in buying NT stocks, okay, or a total wealth of theta in these stocks, okay, and then from that we can consume some amount C of T, okay. And the Merton problem considers we want to maximize the utility of our consumption, okay. We end up with this objective where we discount over time the utility of our consumption, okay. Now, we came up with a solution to this Merton problem. Specifically, we looked at the case where the utility function that we considered as a CARA utility, so constant relative risk aversion, okay, which is a specific form of utility function. And for that, we found some parameters here. Theta, which is the amount of money that we invest in the stock, okay, so it's some proportion of our wealth. And then C, which is our optimal rate of consumption, okay, or as given by some parameter gamma here, okay. Now, we showed that this is a solution for the HJB equation, but we didn't get quite as far as proving rigorously that this is optimal. Okay, so we're going to take a little bit of time just to prove that indeed this is optimal, okay. So this is essential if you want to get a kind of rigorous mathematical proof, though in many ways I'm quite happy if you've come up with a way of solving an HJB equation in the first place, and I'd be, willing to bet money that if you can do that, then you've probably got an optimal solution anyway. But okay, let's go through the rigorous parts of this, and some of these exercises here are intended. Some of these exercises here are intended as homework assignments for some of you, so I'm not going to go through the answers of some of the questions. They're a little bit fiddly, but I'll give you some hints as to how to solve those as well. Okay, so we now give a rigorous argument of optimality of the parameters C star, theta star, and gamma star as above, okay, for the Merton problem with a CARA utility function, okay. So the first thing to ask is to show that if I look at the utility I get out of some policy with consumption C of T, and I compare it with the optimal policy C star of T, okay, then this is less than the expected value of this integral here, where I look at the difference between C of T and C star of T times some multiple times some function zeta of T, okay, which is given by this, all right, okay. So, and the answer to this is fairly straightforward. So we're just going to use the concavity property of our utility function u. So u of C is concave, okay, and the property of concave functions, or indeed the definition of a concave function, is that we can say that u of C is less than u of C star, some other number, plus, I've written y here, C minus C star u dashed of C, okay, star, okay, and that's essentially saying that if I take my concave function and I look at C star and I linearly interpret it by taking the gradient here, then that is going to lie above the value of C. So if I had C star here and I plot u of C and I look at what happens when I take the line from C star to C, then it should lie above the curve, okay? And so that is the one way of defining a concave function, okay? We'll just apply this inside this integral here, okay? So we have the expected value of the integral from 0 to infinity e to the minus rho t, the utility of c of t dt, okay, is less than or equal to the same guy. Okay, now I substitute in this, so get u of c star of t plus c minus c star at time t. Okay, and then times dt. Okay. Oh, and I've forgotten one thing, the derivative here, sorry. U dashed of c star of t. And now all of that dt. Apologies. Okay. Right, and then if I collect this all together, I've got e to the minus rho of t, u dashed c star of t, so that's the zeta term as required, okay? And so I'm going to end up with exactly this plus this, which is what's required, okay? Okay. Another thing to note about this expression, if you just look at the values of c star of t and u dashed, then we're going to get something of this form, okay, for the value of zeta t. So it's just a matter of checking. That's going to become useful because we've got an exponential of a Brownian motion and then it's compensated by the correct term here. Okay. So the next question, exercise, has to verify that this function, so we're looking at kind of integrals, okay, of zeta times cs, okay, to verify that this times zeta t wt is a positive local martingale, okay, and I'm not going to give you the solution because this is a, or at least I'm not going to write it out because this is a homework assignment, but the main hint for this question is that if we look at zeta t wt, then it's essentially proportional to a function that looks like this, wt e to the minus kappa b of t minus r plus kappa. And I think I should have a squared in here, t, okay? And so I can do a bit of Ito's formula to this guy and then find out what happens to some of the drift terms, okay? Remember that something's a local martingale if it's got zero drift when you apply Ito's formula to it, okay? Right. So then the next part, so it asks to show that W0 is less than or equal to E integral 0 to infinity zeta s c of s ds. Okay, and here we can notice that if I look at my function y from here, if I start from 0, this is 0, okay, and I'm just going to get w of t times zeta of 0, which should be equal to 1, okay, that's equal to 1, and the initial rate of consumption we can probably check is equal to 1 as well, okay, alright, so we're going to end up with that, remember that a positive local martingale is indeed a super martingale. Okay, so you should have learnt that from your stochastic integration course. Okay, and you'll also learn from a martingales course about Doomb's martingale convergence theorem, or alternatively by optimal stopping theorem in the super martingale case, positive super martingale case. That we have that W0 is equal to y of naught, which is less than or equal to the infinite time version of our process, okay, which is then going to be equal to e integral from 0 to infinity zeta s c of s ds. Okay, right, okay, right, and just to be double careful, you can check here that this term, as we take things to infinity, this zeta is going to go down to 0 almost shortly, so it's going to go down exponentially fast. So it's going to essentially win out over this wt term. Okay, right. So next part, by direct calculation, show that if we put in c star in here, okay, then we can get this to hold with equality. Okay, so if we put in c star in the same expression, this holds with an equal sign. Okay, and again, that's another exercise for you guys to try out. So again, there's a little bit of a few fiddly steps, but the basic idea is to take this expectation inside here, okay, and look at e of zeta s c star of s. Okay, we have some information about what zeta s and c star look like. Okay, remember from here we've got sort of form that this takes in terms of Brownian motion, and you can use the fact that for a Brownian motion the e of alpha bt minus alpha squared divided by 2t is equal to 1. Okay, so applying it to this formula, okay, this formula to this expression, we should be able to find this calculation works out, and it's just a bit of bookkeeping. It's a little bit fiddly, but that's essentially what's required to show that this holds. Okay. So then we're at the state where we can do the final part of the proof. So this is left as an exercise. Okay. So then the final part, okay, is to note that this holds. Okay, well, we note we've already got an upper bound on e to the minus rho of t u c of t dt minus e integral 0 to infinity e to the minus rho t u c star of t dt. Okay, and then this guy we showed in the first exercise we tried, this is less than this integral, okay, specifically e integral 0 to infinity c of t minus c star of t zeta of t dt, okay, and from our two exercises above, we see that half of that integral is equal to w0 and half of that integral is a bit less than w0. Okay, so what we're going to end up with is something, since this is w0 and this is a little bit less than w0, this is going to end up with something that's negative. Okay, and so c star t must be the optimal rate of consumption, since for any policy this is going to be bigger. Okay, so this is one way of kind of dotting the i's and crossing the t's to prove optimality at that policy. Okay, I wouldn't worry about it too much. I'm more concerned about going about solving the HJB equations in a good way. Okay, all right, great. Well, that's that for now. Okay, yeah.